survey responses on it.
Oh, that is a daunting sight for anyone.
Right, because you've just asked 300 tourists to evaluate their recent vacation. And what you have is this mountain of messy, subjective human emotion.
Absolutely. Frustrations about hotel room service,
Yeah,
delight over a sunset.
exactly. Varying perceptions of safety, complex intentions about whether they'd ever actually return. And the question is, how do you turn that chaos into, well, mathematical certainty?
You really need a powerful tool for that.
You do. So today, for you listening, we are taking a deep dive into a comprehensive guide to SPSS. That's the statistical package for the social sciences. We want to figure out exactly how researchers translate all that messy human behavior into hard data.
It really is the engine room of modern social research. I mean, whether you're in public health, education, business, tourism,
Right.
because you are rarely dealing with perfectly predictable elements like you would in, say, physics or chemistry.
Yeah, you are dealing with people.
Exactly. And SPSS provides the framework to structure that unpredictability, so we can actually test our hypotheses scientifically.
Okay, let's unpack this. What exactly is happening in the software when we upload that giant spreadsheet?
Well,
Because I'm going to play the role of the researcher today, and I'm looking at this wall of numbers, knowing that SPSS doesn't, intuitively understand what a frustrated tourist is.
that is the perfect starting point, really, because you have to translate your concepts into the language of variables before the software can do literally anything.
Okay, so how do we map that out?
In SPSS, your rows are your cases. So
Yeah.
in this instance, each individual tourist is a row.
Got it. Tourist one, tourist two.
Exactly. And your columns are the variables. Now, you already know the basic architecture, right?
Yeah.
The independent variable is the input or the predictor, like the service quality of the hotel.
Right.
And the dependent variable is the outcome, like the tourist's overall satisfaction.
You're causing the effect.
Yes, but the guide emphasizes that SPSS allows us to map out much more realistic, complex human behaviors by introducing mediating and moderating variables.
Right, because if I just draw a straight line from service quality to customer satisfaction, I'm ignoring all the nuance.
You're missing the whole picture.
Let me test an analogy on you here. If I'm building a theoretical model of this tourist experience, the independent variable is like the dial I'm turning, say, investing money to increase service quality.
Okay, I like where this is going.
And the dependent variable is the gauge reacting to it, showing higher satisfaction. So where do mediators and moderators fit into that machine?
What's fascinating here is how the mechanics of those two differ in the software. Think of a mediating variable as the hidden gear inside the machine that actually connects your dial to the gauge.
Hidden gear. Okay.
Yeah, it explains the mechanism of the relationship. Our source uses a classic tourism example. So simply providing good service quality doesn't directly teleport the customer into having, repurchase intent.
Right. They don't just instantly book another trip.
Exactly. Instead, high service quality builds trust.
Ah, okay.
And it is that trust that subsequently drives the repurchase intent. So trust is the mediator. If you remove trust from the model, the connection between the service and the repurchase might completely fall apart.
So the mediator is the stepping stone. The effect passes through it.
Precisely.
Now, contrast that with a moderating variable. If a mediator is an internal gear, is a moderator more like a volume knob that amplifies or mutes the whole system?
That is exactly how you should look at it. A moderating variable doesn't explain the sequence of events.
Right.
It dictates the intensity of the relationship based on different conditions.
Right.
Let's say we're looking at how service quality impacts satisfaction, but we introduce income level as a moderator.
Okay. So how does that change things?
Well, for a luxury traveler with a high income, a tiny drop in service quality might plummet their satisfaction.
Because they expect perfection.
Exactly. But for a budget backpacker, that same drop in service quality might barely register. The relationship between service and satisfaction exists for both, but the income level turns the volume of that relationship up or down.
Which is highly practical if you're like a hotel manager trying to figure out which market segment to actually target.
Absolutely.
But this brings up a mechanical problem. I know I want to measure trust, satisfaction, and income level, but if I just feed a bunch of random numbers into SPSS, the software has no context.
Not at all.
It doesn't know if a number one means category one or $1 or first place.
Precisely. And feeding the software the wrong data structure is the fastest way to generate mathematically perfect nonsense.
Garbage in, garbage out.
Always. Yeah, this is why researchers have to strictly define the hierarchy of measurement scales for every single column in their data set. SPSS categorizes data fundamentally into nominal, ordinal, and scale variables.
And scale encompasses interval and ratio data, right?
Yeah, exactly.
Let's bypass the basic textbook definitions and look at the actual mathematical limitations SPSS enforces based on these scales. Because the scale dictates what statistical tools you're even allowed to pull out of the toolbox, isn't it?
It completely dictates your options. Let's start at the bottom of the mathematical hierarchy. Nominal data.
Okay.
This is pure categorization, gender, nationality, or whether a tourist prefers a beach or a city.
So if I code beach as 1 and city as 2 in SPSS,
You cannot ask the software to calculate the mean. An average preference of 1.5 is meaningless.
right, there is no halfway point between beach and city.
Exactly. You are restricted to frequencies and percentages, just counting how many people are in each bucket.
Okay, so then you step up to ordinal data, where you introduce ranking. Education level, for instance, high school, university, postgraduate. We know the direction. Postgraduate is higher than high school. But the psychological or temporal distance between those ranks isn't a fixed measurable unit.
Right, it's not like measuring inches.
So again, asking SPSS for a precise average education level is mathematically dubious.
Which brings us to the top tier, interval and ratio data, which SPSS lumps together under the term scale.
Okay.
This is where you have equal distances between points, and in the case of ratio, a true zero.
Like age or income in dollars or nights stayed at the hotel.
Yes, because a dollar is always a dollar and 0 nights means no stay at all. SPSS unlocks its full arsenal here. You can run means, standard deviations, and complex predictive models.
Now, I have to bring up the elephant in the room regarding social science research, which is the Likert scale.
Oh, the Likert scale, yes.
It is everywhere. You give someone a statement and ask them to rate it from 1, strongly disagree, to 5, strongly agree.
A staple of surveys.
Strictly speaking, that is ordinal data. The psychological distance between neutral and agree might not be the exact same as the distance between agree and strongly agree.
That is a very fair point.
But in practically every paper I read, researchers are treating these 1 to 5 surveys as continuous scale data. We're basically just tricking SPSS.
It is a calculated compromise.
Yeah.
You are correct that a single Likert item is ordinal, but the text clarifies a crucial methodology. Researchers rarely rely on a single question.
Right, they ask a bunch.
They ask 5 or 6 different Likert questions around a single concept, like hotel cleanliness, and then they average those scores together.
Ah, I see.
By creating that composite index, the data behaves much more like a continuous scale. And making that leap allows researchers to calculate the mean and the standard deviation.
Which are the lifeblood of advanced statistics.
Exactly.
It lets us measure not just the center of opinion, but the consensus. Like if the average satisfaction is 4.2 with a tiny standard deviation, everyone agrees.
Yes.
If the average is 4.2, but the standard deviation is huge, the data is polarized. But that composite index trick relies on a massive assumption, doesn't it? That all 6 of those questions are actually measuring the same thing accurately.
And that leads directly to the concepts of reliability and validity. You cannot just average a bunch of survey questions, dump them into SPSS, and start running predictive models.
You have to prove the data is trustworthy first.
Exactly.
I see this constantly conflated, reliability versus validity.
It happens all the time.
So if I have a broken bathroom scale that always says I weigh exactly 150 pounds, it is incredibly reliable.
Right.
Because it gives me the exact same consistent number every single time I step on it. But it has absolutely zero validity because it's not measuring my actual true weight.
That is the exact dilemma. In SPSS, we prove reliability, the consistency of your survey, using a metric called Cronbach's alpha.
Cronbach's alpha.
Yes. It looks at all your Likert questions for a specific concept and checks how closely the answers correlate with each other.
Okay.
The guide sets the baseline here. You want a Cronbach's alpha of at least 0.70, though 0.80 and above is considered good to excellent.
So I'm looking at Cronbach's alpha to check reliability, and I see a score of 0.95. Most people would celebrate. But isn't there a danger in chasing that number?
What do you mean?
If my score is practically 1.0, doesn't that just mean I'm asking my tourists the exact same question 10 different ways and boring them to tears?
Yes. That is a phenomenon known as redundancy. If your alpha is too high, you aren't capturing a nuanced concept. You are just repeating yourself.
Makes sense.
But assuming your alpha is in that healthy 0.80 range, your survey is reliable. The harder part, as you pointed out with your broken scale, is proving validity.
Right. Is your hotel satisfaction survey actually measuring satisfaction, or is it accidentally measuring the tourist's perception of the hotel's luxury level?
Exactly.
To solve that, researchers usually just throw a ton of questions at the wall. Let's say I give my tourists 20 different statements to rate, trying to capture every facet of service quality,
Staff empathy, room cleanliness.
check-in speed, food temperature, yeah. But analyzing 20 separate variables is a total nightmare. This is where factor analysis comes in, right?
Factor analysis is arguably one of the most powerful tools in SPSS for survey design. It takes your 20 sprawling questions and analyzes the covariance matrix.
Which means
It's essentially looking at how every single question correlates with every other question simultaneously. It looks for hidden dimensions.
oh, wow.
Yeah, it might mathematically reveal that questions 1 through 5 all clump together around a hidden factor we'll call tangibles, while questions 6 through 12 clump around a factor called empathy.
It reduces the noise. It tells me I don't have 20 variables. I actually just have 3 underlying themes.
Precisely.
But SPSS isn't magic. It won't just group things perfectly every time. What are the mechanical triggers I need to look for to know if my data can even be factored?
The software forces you to pass 2 checkpoints before you can trust a factor analysis. First is the Kaiser-Meyer-Olkin measure, or KMO.
KMO, got it.
This checks if your sample is adequate and if the partial correlations among your variables are strong enough. The text specifies you need a KMO value above 0.60, though ideally much higher.
And the second checkpoint.
The Bartlett test of sphericity. This sounds intimidating, but it's simply checking your data against an identity matrix.
Okay, in plain English.
It is proving that your 20 variables aren't just completely unrelated random numbers. You need a p-value of less than 0.05 on the Bartlett test.
Right.
If you pass the KMO in the Bartlett test, SPSS is giving you the green light that your data has enough hidden structure to be grouped into clean, manageable factors.
So the data is structured, it's reliable, it's valid, and it's factored down into manageable dimensions. Now we actually want to test our hypotheses.
Yes.
We want to find differences and make predictions. Which brings us to the great divide in statistical testing: parametric versus non-parametric tests.
It is the fork in the road every single researcher must navigate. Parametric tests, like your t-tests and NOVAs, are mathematically powerful.
Right.
They are highly sensitive and great at detecting subtle relationships, but they demand strict toll. Your data must be continuous scale data, and it must follow a normal distribution.
We aren't going to re-explain the bell curve here because anyone touching SPSS knows what a normal distribution looks like. But how does SPSS explicitly define normal mathematically? Because, perfectly normal data doesn't exist in the wild.
It doesn't. And if you rely on visual histograms, human bias will convince you your messy data looks, normal enough.
Oh, for sure. So we rely on skewness and kurtosis. Skewness measures the asymmetry. Is your data leaning too heavily to the left or right?
And kurtosis.
Kurtosis measures the tails. Is your curve too peaked or too flat compared to a normal distribution? The guide provides the accepted thresholds for social sciences. If your skewness and kurtosis values fall between -1 and +1, the data is considered sufficiently normal.
And why does SPSS care so much about that? If my data is highly skewed, say a skewness of 2.5, why can't I just run a parametric test anyway?
Because the entire mathematical engine of a parametric test relies on the mean and the variance. If your data is massively skewed, the mean is dragged away from the center.
So it no longer accurately represents the typical response.
Exactly. If you feed a distorted mean into a t-test, the t-test will spit out a distorted, untrustworthy result. So if my skewness is completely out of bounds, or if my data is strictly ordinal and I can't calculate a mean at all, I'm locked out. I have to use non-parametric tests.
Exactly. Tests like the Mann-Whitney U or the Spearman correlation, these are your safety nets.
Okay.
They don't care about bell curves or means. They work by converting all your raw data into ranks: first, second, third, all the way to 300, and then analyzing the ranks.
That's clever.
They are incredibly robust against outliers and messy data, but the trade-off is a loss of statistical power. They might miss a subtle effect that a parametric test would have caught.
Here's where it gets really interesting. Let's assume my data behaved perfectly. Beautifully normal, skewness is 0.2. I'm in parametric territory.
Lucky you.
Right. I want to compare groups to see if their satisfaction levels differ. If I am comparing my male tourists to my female tourists, I know I run an independent samples test.
Yep.
It looks at the means of the two groups, looks at the spread, and tells me if the difference is real. But what happens when the design gets more complex? Say I want to compare satisfaction across 3 groups: budget, mid-range, and luxury tourists.
The instinct is to just run 3 separate t-tests.
Yeah.
Budget versus mid-range, Mid-range versus luxury, budget versus luxury.
Yeah, why not?
But doing that inflates your risk of finding a false positive. Instead, the software requires you to use an ANOVA, an analysis of variance.
Nova.
ANOVA evaluates all three groups simultaneously by comparing the variance between the groups to the variance within the groups.
But there's a catch with ANOVA. The math tells me that a difference exists somewhere in the mix, but it doesn't explicitly tell me where.
That is the inherent limitation of the F statistic that ANOVA produces. It acts as an overall alarm system.
Okay.
If it triggers, it simply means, hey, at least two of these groups are significantly different from each other.
But to do the forensic work of finding out exactly which ones differ, you must run a post hoc test.
Yes. The text highlights the Tukey test, which essentially goes back in, controls for the error rate, and compares every possible pair to pinpoint exactly where the significant differences lie.
Finding out that luxury tourists are more satisfied than budget tourists is useful, but it's just comparing averages.
Right.
The holy grail of social science is prediction. We want to know how much one variable explains another. Like, does spending more money on staff training directly predict higher customer satisfaction?
And that elevates us to regression analysis.
Right.
We are no longer just looking for differences. We are building a predictive model.
Okay.
The most crucial output to look for in your SPSS regression table is R squared.
Let's ground that number. If I run my regression model predicting tourist satisfaction based on service quality and perceived safety, and SPSS spits out an R squared of 0.48, what am I literally telling the board of directors?
You are telling them that 48% of the total variation in customer satisfaction is explicitly explained by the service quality and safety metric you measured.
Wow, okay.
The model accounts for almost half of their decision-making process.
Which humbles us, really, because it means the other 52% of their satisfaction is driven by variables we didn't put in the model. Weather, travel fatigue, the exchange rate.
Exactly. It forces you to acknowledge the limits of your research.
Now, we can't do a deep dive on statistics without addressing the ultimate gatekeeper of academic publishing, the p-value.
Yes, the p-value.
Every single test we've discussed today, from ANOVAs to regressions, we are looking for that magical p less than 0.05.
It is the threshold for statistical significance rooted in the logic of the null hypothesis. We always start by mathematically assuming there is no effect.
That service quality has absolutely zero impact on satisfaction.
Exactly. The p-value is the probability of seeing your specific survey results if that null hypothesis were completely true.
So a p-value of 0.03 means there's only a 3% chance that I would get these results purely by random fluke. Since that is less than the 5% threshold, I reject the null hypothesis. The effect is real. But listen, I want to push back on the worship of the p-value here.
Go for it.
I've read studies with massive sample sizes, say 50,000 people, where the p-value is 0.001, highly significant.
Right.
But when you look at the actual data, the difference in satisfaction between two groups is like 0.02 on a 5-point scale.
This raises an important question, and the guide explicitly warns researchers about this exact trap. A tiny p-value only proves that an effect exists mathematically.
Okay.
It proves it is not a fluke. With a sample size of 50,000, SPSS has so much data that they can detect microscopic, mathematically real differences that have absolutely zero practical value in the real world.
It's scientifically significant, but practically useless.
Exactly. This is why modern statistical standards require you to report effect size alongside your p-value.
Like Cohen's d.
Yes, metrics like Cohen's d or eta squared tell you the actual magnitude of the difference. The p-value tells you if you should care. The effect size tells you how much you should care.
So, mapping our journey today for everyone listening. We've taken chaotic human experiences and assigned them to nominal, ordinal, and scale variables.
We have.
We've managed mediators and moderators. We've proved our Likert data is reliable with Cronbach's alpha and valid through factor analysis.
Right.
We checked our skewness to unlock powerful parametric tests like ANOVA, and we've built regressions that predict outcomes while we're skeptical of relying solely on p-values without effect sizes.
It is a rigorous pipeline, but when you understand the mechanics at each step, the software stops being a black box.
As the statistician, what is the core philosophy you want a researcher to hold on to when they open this software?
It comes back to the core premise of the guide. SPSS is just a calculator. It's a highly advanced calculator, but it only executes the mathematical commands you give it.
Right.
The researcher determines the research problem. The researcher defines the parameters of the variables. The researcher checks the assumptions of the tests.
So it's all on us.
If you ask a flawed question or categorize your data poorly, SPSS will not stop you. It will happily process the data and hand you a beautifully formatted, mathematically flawless, entirely incorrect conclusion. The software doesn't do the science. You do.
It's basically a really fast, highly obedient pencil. You listening to this, you now have the conceptual blueprint to navigate this methodology. You know why an ANOVA analyzes variance, why factor analysis collapses dimensions, and why a p-value isn't the whole story. But as we wrapped up this deep dive, I want to leave you with one final thought to ponder. If a software suite like SPSS is capable of finding mathematically perfect, statistically significant patterns in whatever numbers we feed it,
Which it is.
how much of our objective social science is ultimately shaped by the highly subjective, deeply human biases we use to define the variables in the very first place?